So good afternoon. Welcome to BIDMC Connect. My name is Gyöngyi Zabó, Chief Academic Officer. So today is going to be a little different. We're going to talk about translational medicine learning and artificial intelligence. This is my great pleasure to welcome and introduce Dr. Stephen Horng, who is a dual board certified physician in emergency medicine and critical informatics, who has degrees in computer sciences and biomedical informatics. He specializes in translational clinical informatics and focuses his research on novel methods of artificial intelligence to improve the quality and efficiency of critical care and clinical care in general. Especially, he works on applying state-of-the-art machine learning methods to bedside care, as well as developing next-generation medicine learning algorithms to make sense of the information found in electronic health records. He is the clinical lead for machine learning at the Center of Healthcare Delivery Sciences here at BIDMC, a cross-departmental center to advance machine learning throughout the entire medical center. Dr. Horng is the program director of the Clinical Informatics Training Program at BIDMC, which is an ACGME accredited training program and an NIH T15 training site in biomedical informatics. We're very much looking forward to his talk, and Steve, thank you for being here today.
Thank you, and it's really a pleasure to be able to address such a wide and varied audience. My obligatory disclosure slide: I get funding from Philips Healthcare, Doris Duke Charitable Foundation, Mass Life Sciences, and the MIT J Clinic. And some of that work is featured within this presentation, but I don't believe there's any commercial bias to any of this. So as we said, my area of research is really around translational machine learning. I started my career here at the BI as a fellow and really on the operational side of things around EHR programming and really day-to-day operational needs within IS. And within the last couple of years, my kind of research focus has really been around machine learning research, and specifically around translational machine learning. So how do you take these advances within computer science and machine learning, and how do you translate them to direct clinical care? And then how do you take those lessons that you learned from deploying machine learning to clinical care and bring that back to what are basic science researchers in computer science? So very similar to translational medicine, but swap bench-side research with computer science folks. And so that's kind of the world that I live in these days. So I'm gonna kind of split my talk into 4 parts. First, I'll talk a little bit about recent advances in machine learning and why healthcare is different from all these other domains. And then I'll talk about some different mitigation strategies of how to use machine learning in healthcare despite all these challenges. Everything from positive and unlabeled learning to semi-supervised learning, transfer learning, multitask learning, multimodal learning, just different ways of getting around some of these limitations. And then a couple of practical applications of machine learning that are currently deployed and live at BIDMC that's taking care of patients. And then lastly, some open questions that still remain within machine learning for healthcare. So to start, machine learning, it's really revolutionized how we think about what computers can do. But healthcare is quite different. So machine learning, or just computation, machine learning in general, has been around for a very long time. This only goes back to 1993, but this is a slide around speech recognition, which is a type of machine learning that takes speech and turns it into text. You can see on the y-axis here is a log scale of the number of errors, and you can see over time that the error rate has really dramatically reduced. So back in 1993, really a huge number of errors, and in 2016, you're way below the human error rate. And so in fact, computers are doing better than humans can do in this task, in speech-to-text recognition. And we're seeing that throughout machine learning. This is ImageNet, so a task of taking pictures and identifying things within that picture. So you can see here around the red box, this is a dog. Around the yellow box, this is a child, this is a chair, etc. In 2011, you can see the error rate was a 25% error rate. And in 2015, for the first time, you can see that computers were doing better than humans at identifying things in pictures. And so just like speech recognition started doing better than humans, so did machine vision. This has a lot to do with two main things. One is the availability of large amounts of data, and two is really large computational power. Most of these advances have been around deep learning. So what is deep learning? If you remember from Biology 101, on the left is a neural network. So you can think of it as you have some neurons that are at the input layer. They are all connected to some sort of intermediary neuron layer, and then you have some outputs on the other side. So this is a shallow neural network. This has been around since, I don't know, the 70s or 80s for a very, very long time, of a biologically inspired machine learning method where you have maybe one, maybe two, rarely more than 3 or 4 layers in your hidden layers. And so what are called shallow neural networks, where every neuron in one layer is connected to every layer in the subsequent layers. And so it's called a fully connected network. The problem with these fully connected networks is as you increase the number of layers, you can see here, this is a 4-layer network. But as you increase them more and more, or said in a different way, as you go deeper and deeper, the number of connections here really rises drastically. And it's both computationally inefficient, but also really, really prone to overfitting. Now, the nice thing about neural networks is it allows you to learn these really interesting nonlinear relationships, something that regressions or other types of linear models just can't do. So neural networks, especially being biologically inspired, have been a really hot and interesting topic, but have not really shown their promise until really the most recent years. And this is because we started doing something different. Not only were these networks really deep, and by deep I mean hundreds of layers deep, we started doing convolutions. So no longer are each neuron connected to every other neuron in the next layer down, but they're only connected to some. And we started doing some nonlinear transformations, things like max pooling and other such functions, so that as you go from one layer to the next, things get more and more abstract. So you can think of this as you start with an image, and at every layer down, you're learning a more abstract representation of that image. So the first layer could be something like a pixel, the next one could be a line, the next abstract layer is, well, lines form corners, corners form shapes, shapes form faces, and then etc. And so the nice thing about these convolutional neural networks is, one, there's much fewer connections, and two, it automatically starts to create these abstractions in a really automated way. So rather than trying to craft your features, craft your variables, you're letting the algorithm do that for you. And then finally, at the last couple of steps, you have, again, your fully connected network, and then whatever task you're trying to do, whether it's classification or regression. So this type of architecture really underpins a lot of the different types of advances within machine learning in the last couple of years, with some modifications here and there. It's really this ability to abstract things out. So just as we've seen these improvements in speech recognition and image recognition, folks have taken those same types of methods and applied them to similar tasks, such as identifying diabetic retinopathy on fundus photographs, retinal photographs. So this is a team from I believe this was the Google group, who took a whole bunch of images, labeled a lot of them, and in fact were able to predict diabetic retinopathy versus normal at a much better rate than trained ophthalmologists, than board certified ophthalmologists. And similarly, this group from Stanford did a similar thing on EKGs, trying to identify atrial fibrillation from the EKG, again using a convolutional neural network, this time 34 layers. And they were able to do this better than a board certified cardiologist. And so now we have, and you'll see an example of this over and over again, that these deep learning algorithms are doing better than board certified specialists and sometimes subspecialists. So great, we have all of these advancements. Why then aren't we making more progress? Why is healthcare really lagging behind all these other areas, and why hasn't this become really widespread across all of medicine? And so I thought I'd give this example of an EKG. So this is an EKG of a patient, and on the bottom is a typical read that a cardiologist would document, and it would say something like, this patient has a right ulnar branch block, and alert, there is a inferior posterior myocardial infarction. So this patient is having a heart attack. Now, what's documented is on the bottom, but what's actually found in this EKG is a couple of things that aren't actually mentioned. So there are ST elevations, sure, but there's also an RSR prime, there's a Q wave in here, and there's a whole bunch of different normal findings. They're not documented at all. So I thought this would really illustrate the point that EHR data, or just clinical data in general, isn't collected for research. It's not meant for data scientists and other researchers to use. It's collected for clinical reasons, billing reasons, and operational reasons. And so that data is highly biased. It's highly biased in that we often only record positive labels, and oftentimes only the most severe of those positive labels, and we just assume some of the other labels because it's obvious from a trained clinician that those things must also exist. Secondly, healthcare is really different than all these other domains in that the number of labels that we have on our data is really small. When you look at those other examples, ImageNet for machine vision, you're talking about millions, actually no more than billions, like billions of images that were labeled. Compare that to medicine, where we're talking about sample sizes of thousands, and if you're lucky, hundreds of thousands. But these are really many, many orders of magnitude smaller than other computer science tasks. That labeling that is done is often biased, noisy, incomplete, and unstructured, which makes life really quite difficult for these machine learning algorithms. So given all these challenges, how do we get beyond this? How are we able to make any progress? Well, in the prior examples, in diabetic retinopathy, for example, they got around this by having a lot of money and paying a lot of people, a lot of expensive clinicians to label that data. Or there are just edge cases where it's easier to extract gold standard labels. But for the vast majority of almost all clinical tasks, those labels just don't exist. So how do you learn when the labels that you have are noisy, incomplete, and biased? So one of our really early works, and this is around 2014, we started exploring this world of learning using positive-only labels. In EHRs, for example, you might carry a diagnosis code of heart failure, hypertension, and a lot of different problems. Now, these are only positive labels. You'll never find an example where you have a diagnosis code of the patient doesn't have hypertension, or the patient doesn't have Y or Z. So how do you learn when you only have positive labels and you don't have the counterfactual, you don't have the negative ones, and if you do have the negative ones, you have a bias of not recording them. So we took this pilot and we tried to train a bunch of different classifiers using ICD-10 codes and other information that were consistent with infection. And as features for that model, we used vital signs in labs. So for example, if you had an ICD-10 code of pneumonia or UTI, then that was positive. If you didn't have those ICD-10 codes, then it was negative. And we try to predict if you had an infection or not, depending if you had a fever, you had a positive UA, you had a white count, etc. And we compared two different methods. One that said, which is the supervised baseline, which says if we take everything that was positive and say it's positive, and take everything else that wasn't positive and said it was negative, and train a model, how well does that do? And then we compared it to this other method, which is called positive and unlabeled learning. And we said, well, if it's positive, it's definitely positive. But if we don't observe it, then we actually don't know. It could be positive or negative, and then somewhat negative, and those are definitely negative. So on this slide, you'll see that in blue is the positive and unlabeled learning, what we call anchor-based learning, and in the dotted green is this supervised baseline. The x-axis is the amount of time that's elapsed in an emergency department stay. So as you go from left to right, left you have very little data to use. As you go to the right, you have more and more data. And you can see that this positive and unlabeled learning method, this anchor-based learning method, really substantially does better than the supervised baseline. So rather than just using logistic regression, for example, using this other method that helps correct for these unlabeled examples, you do remarkably better. Use cases of this are a lot. We use ICD-10 codes and other things for things like cohort selection, for research screening eligibility, to find patients like this for risk adjustment and other such things. And so using this type of method allows you to maybe not completely fix the bias in the labeling, but it allows you to help mitigate it quite substantially, especially when you have a smaller amount of data. So the first mitigation strategy, well, is how do you deal with positive only data? The second one is, and the more fundamental one is, how do you deal with data when almost nothing is labeled and the amount of data that you have is very small? Because these modern machine learning methods really require orders of magnitude more data than we currently have. So this brings up this area of learning called semi-supervised learning. So if you recall, we have a class of models called supervised learning. That's where you know the outcome of interest. So for example, if you were trying to predict whether a patient has cancer or not. Having a blue or yellow dot here, you know the outcome of interest, and you can use a model like logistic regression, a support vector machine, a decision tree. These are all different types of supervised learning because you know the outcome. On the other hand, there's another class of models called unsupervised models where you don't know the outcome of interest. All you know are things about that patient. So you know their laboratory results, you know the medications, but you don't actually know their outcome. And can you cluster them together, clustering them on in areas that kind of look alike? And so different things like principal component analysis, k-means clustering, topic modeling, etc., are types of unsupervised learning. So one way of getting around this lack of enough labeled data is, well, can we first learn something from all this unlabeled data, and then try to learn and then use supervised learning? So using the advantage of a large sample size that's unlabeled, and then using a supervised model on top of that. So one way of conceptualizing this is, well, you have all this data, and you probably don't want to waste your statistical power in learning relationships between BUN and creatinine, or height and weight, or these or other such correlations between your features. And can you instead use unsupervised learning to learn these relationships so you can use your statistical power to learn the outcome of interest instead? And so that's what semi-supervised learning is. Doing some sort of unsupervised learning first and some supervised learning after that. And when you learn this unsupervised model, you probably want to learn something that's somewhat rooted in reality. There's a type of model, or there's a class of models that are generative models. That says that there's some latent space, some unobserved entity that could perfectly generate whatever you're observing. So on the right-hand side are some examples of different faces, and down the column are potential different latent variables. So dimensions of interest for that face. One could be gender, one could be age, hairline, mouth being open, wavy hair, having a beard, or glasses. And what you might, in a generative model, you could take any of those dimensions and move them up or down and generate an image that represented that. So as you can see here, as gender goes this way, this picture becomes a female. As you change the latent variable this way, they become a male. Here, if you go this way, their mouth is closed. If you go here, their mouth is open. Same thing for wavy hair, beard, and glasses. So it's just a different mentality, which says you have some underlying representation that represents these variables that you don't know about, but you could generate whatever you're seeing because of it. So that's what topic modeling is as well. So if you have a whole lot of text and you knew what types of topics were in that text, then you could generate a statistically accurate version of that text based on those topics. So that's what generative models are. So if you could do this along with semi-supervised learning, then maybe you could do something pretty interesting. So this gets us into area of deep learning called, really one of the advances in the last couple of years has been around variational autoencoders. So you have X here, which is, if you go back to the picture example, you have the original image, and you try to train a model which creates a latent representation Z, which can then recreate that picture perfectly. So you take a picture, you encode it into some latent representation, and then you decode it back, and you try to make X and X prime, so the original image and then the reconstructed image, to be the same. You probably want to add a little bit of noise, and that's what this is, some noising function, so it's not exact. And if you do this really well, then you can take a picture and recreate it. And so you know Z, that latent representation has to be pretty good because you're able to recreate the picture that you had. Now, as you get like these really large deep learning networks, you can think of it almost like overfitting, right? There's like an infinite number of this space Z, which could fulfill this criteria, but at least it's smaller than if you didn't like do this autoencoder mechanism. So we did this to chest X-rays, except we also, so here is the same thing, illustrated a little bit in a little bit different way. You have X here, which is the original image, X prime, which is the reconstructed input, Z, which is this latent space. So you can think of Z here, we're going to use that as an example, chest radiographs. So some latent variables in the space of chest radiographs could be, the size of your heart, whether or not you have pneumonia or not, whether or not you have fluid overload or not, etc. And you could describe that picture as a probability distribution over each of those Z's. So you can think of it almost like a telephone. If you had a person over here and they wanted to tell a person over here that to be able to tell them to describe how to draw that picture, then you need some way of encoding it, and then for this other person to decode it. So you have a picture of a car here, and the person might say, well, this car has 4 tires, it's blue, it's a Toyota, and it has a V6 engine or something like that. And then the person over here will listen to that, decode that message, and try to redraw that picture. Now, a really good model would be one where it has really good reconstruction loss so that the original image and the reconstructed image look pretty similar, but also so that if you take this latent representation Z and you try to use it to predict your actual outcome that you care about, Y, then it also does similarly well. So a good representation Z both minimizes this reconstruction loss, so the difference between the original and reconstructed image, and it reduces the prediction loss. So in our example, we wanted a way of predicting the severity of pulmonary edema on a chest radiograph. Something that's, as you can see, we started with a data set of 220,000 images, 220,000 chest radiographs, but only around 3,000 of those chest radiographs were actually labeled. And so really a very small sample size to do deep learning with. And so we use this semi-supervised learning approach using variational autoencoders, trying to optimize that latent space Z in order to classify them into pulmonary edema severity levels. 0 being no pulmonary edema, 3 being severe, 1 and 2 being mild and moderate. And so you can see the AUCs, these are receiver operating characteristic curves, and you can see that these models do remarkably well. AUCs of anywhere from 0.7 to 0.99 in being able to classify them into mild, moderate, and severe. So this is joint work with Seth Berkowitz in the Department of Radiology, as well as Ray Z. Lau and from Kalina Golan's lab at MIT, as well as the Phillips Research Lab. And you can see that this task, without doing this semi-supervised learning, would have been impossible. If you took a straight up supervised learning approach using 3,000 labels, you wouldn't have gotten anywhere. And so we learned a representation from all these other chest radiographs that weren't labeled. And then we used that learned representation. So it's a type of representational learning. And we took that learned latent space Z and we built a model to predict the thing that we actually cared about. And so that's really one area that really kind of revolutionized how we were doing machine vision, and in fact has beat every machine vision algorithm out there. Now, instead of training this latent space Z on chest radiographs, what if instead we trained it on any random type of image? So what if we instead took that original database of random pictures of things that were labeled with dogs and cats and chairs, and we used the first part of that model. So the first, couple of hundred layers, and then we just chopped off the end of it. So the actual classification layer. So we took the intermediary representation that got to a nice latent space Z, and we took that first part, and then we added a couple of morphoid connected layers over here, and we tried to actually predict what we cared about. So this is called transfer learning or fine-tuning of the existing model. And so we took this approach as well. As you can imagine, this probably shouldn't work that well because you're training on things like dogs and cats when you're actually trying to predict pulmonary edema on a chest radiograph. So you would think this wouldn't work well because these target domains have nothing to do with one another. On one, you have lines and three-dimensionality, and not three-dimensional. You have lines and shades and colors and textures. On the other, you have a radiograph. But in fact, it does relatively well. And so on the left-hand side, you'll see the semi-supervised learning algorithms that were trained on chest radiographs. And on the right, you'll see the same thing, but now trained on random natural images. So fine-tuning, billions of images, or fine-tuning a latent space that was trained on billions of images of dogs and cats versus hundreds of thousands of images trained on chest radiographs. And you'll see that the performance, the AUC is relatively similar, although I'll tell you that the kappa scores on the semi-supervised learning just edge out the pre-trained model. So the ones trained on dogs and cats, barely. We can't quite say for sure that it is definitely better. It's leaning towards it as you kind of think it would, as training on radiographs should be better than training on dogs and cats. One would think. So just as we do in medicine, if you want to teach someone to read a chest radiograph for pulmonary edema, why don't you also teach them how to read a chest radiograph for pneumonia, pneumothorax, and other pathologies in the lungs? And that way you can kind of compare and contrast. So this brings up a third kind of strategy, which is multitask learning. So just as before, we tried to minimize reconstruction loss here, and we tried to optimize prediction loss for pulmonary edema. Why don't we jointly try to optimize for all these other diseases as well? So minimizing prediction losses for pulmonary edema, pneumonia, pneumothorax, etc., and just trying to minimize for all of them. So the logic goes, a good latent space, a good representation learning of this space, if it's done well, should be able to predict any of these different pathologies. And if you aren't, then it's probably overfit for that one particular use case. So this particular technique of multitask learning is quite successful in pretty much every other domain out there in machine learning. We think it'll do well in this particular task as well, although we don't quite have results quite yet. So the last kind of strategy that I'm going to talk about is something called multimodal learning. One way of making use of all this, of making use of data when you have no labels and very little data, is to maybe use some other data set out there, or a data set that's unlabeled. But what about instead using a data set from the same patient population that's correlated with the task that you're trying to do? So in this example, we had chest radiographs, the actual images, but what if instead we tried to, in parallel, train a text classifier? So on the left-hand side, you have the images, you've got the encoder, decoder, and you have Z. So now you encode it and you use an image classifier, and you try to classify the image, call me a gamma, yes or no. And then at the same time, you have a deep learning model doing the same thing, but with the text. And the way this goes is, well, you have these two parallel tracks, and a good latent representation would be one where those two latent spaces kind of live together. Said in a different way, if you have an image finding of pneumonia on a chest radiograph, then you would think that somewhere in that text, someone would mention something about pneumonia as well, right? So even though you don't know that these pixels are equated to that text, they really should co-occur in the same patient on that same image, right? So you have two different projections of the same thing, and so since these two different modalities are correlated, then can we create some sort of joint optimization function where you try to make sure those things are close? And the way we did that is with what are called imposter pairs. So we took images from, we took an image and a text pair. So you had a radiograph taken, and then you had a radiology report. So that's a pair. That's a true pair. Then you create a random imposter pair. So the image from a particular study, and then some other random report text that doesn't have to do with that image, and you pair those together. And in a good representation, those true pairs should lie kind of close together, and those fake pairs, those imposter pairs, should lie really far apart in that latent space. And so if you optimize in this way, it is another way of selecting a good latent representation. So another way of doing representational learning. And so the nice thing is, at inference time, during runtime, you don't actually need the text. All you need are the images. So it's, as an analogy, this isn't actually right, but as an analogy, you could think of this almost like regularization or regularization of the latent space. So a way of selecting from all these different possible latent spaces a better one. And so that's what this does. And you can see on the bottom, image only is the prior example. If we only use images alone, AUC is around 0.74 to 0.78. And you can see if you do this multimodal learning, that in fact, it really improves this model's efficiency quite dramatically, going from 0.74 to 0.82, 0.73 to 0.81, and 0.78 to 0.90. So all we're doing is we're taking correlated modalities, and we're learning them together, even though you don't need all of them, even though you don't actually need all of them at inference time during runtime. So it's really kind of an exciting field. You can kind of see the correlates throughout medicine, where we have multiple representations of the same thing. For example, you could have things like blood pressure, laboratory results, etc., that are expressed in the phenotype. But then you might also have a metabolomic representation of that as well. And then underlying that, you might have some genomic representation of it. And so you could do some multimodal learning because they're all kind of representing similar things, and you use it to train in a way that is much more effective when you have such few samples. And so that's multimodal learning, quite a interesting new field that is going to have really dramatic impact in machine learning for healthcare. So the next kind of part of my talk, I'm going to talk about some things that we've already deployed. So if you take these positive only learning methods, these semi-supervised learning methods, et cetera, and you deploy them, how well do they do, and how do they change workflow? How do they change how we think about patients? The first one I'm going to talk about is the first example that we gave, which was positive only learning, or positive only labels, what was called PU learning. And if we use that model, can we use it to trigger things like alerts and reminders, decision support, clinical pathways, order sets, contextual information retrieval, and research screening? So one of the problem or difficulties in informatics is you build this great tool, you build this great intervention, but no one knows it exists. Or you're running this great clinical trial, but you can't find the patients that might be eligible for it. And so is there a better way? So we use this positive only learning method, and we used it to trigger all these downstream things. And we do it for things like triggering order sets. So rather than having to know that this specialized order set exists, we predict that this patient might have something cardiac going on with them, and we automatically pull up this order set so that users don't have to find it, it's just there. On the right-hand side, we think this patient might benefit from the CHAS2-VASc score as a risk prediction tool, and so why don't we use these machine learning models to trigger that. And then lastly, we use it for things like contextual information retrieval. We think you have a cardiac complaint, and so why don't we pull and extract and summarize all the things that you might need to make a decision about someone that has a cardiac complaint from all the records that we have. And so a way of using positive only learning that we've deployed, and on the bottom is a link or is a reference to some of that work. The next one I'm going to talk about is record linkage, which is a pretty common task when you're dealing with medical data. You have a lot of different systems that have different identifiers. You have patients that cross from hospitals to nursing homes, claims databases, et cetera, where data is kind of fragmented across all these databases. And how do you link those records together? We've all heard of the two identifier rule, using two separate identifiers, name, date of birth, social security number, et cetera. And if you have two or more matches, then it's probably a match. And that's what the bottom represents. This is using those kinds of methods, you get somewhere between 14 and 83% sensitivity to make a match between a pre-hospital record, so an EMS record, and a hospital record. So not at 14%, not great. What we did is we built a machine learning model. In this example, it's a logistic regression model with L2 regularization. We did a whole lot of computed features where we took things like edit distances, the amount of change between ages between two pairs, et cetera, and we built a model. And you can see that we did quite well. Comparison sensitivities were 14 to 83%. Our sensitivity for this model was 99.4% with an AUC of 0.99 and a positive predicted value of 99.999. In fact, in our retrospective review, the only patients we missed were two patients, which was a father-son combo, where the father's MRN was recorded for the son, and the son had the father's, the social security number for the father was given to the son, and the son had the father's accidentally recorded, and their date of births, and their names are very similar, with the same first initial and the same last name. And so our model got it wrong, although one could, say that in fact that is not really an error. Someone recorded their social security numbers wrong. And so this is how we link patients here at the VI in our emergency department to EMS. And it allows us to do some really interesting things. For example, on the top is, so this is the screen of vital signs in a triage note in the emergency department. And you can see we can start to merge records from different places just as if we had done those things. So just as we record vital signs here, we record or we display blood pressures, heart rate, and glucose that was done by EMS. We have medications that we did here, and these are medications given by EMS. And so one view across all these different data sources, because we can be really confident that those matches are pretty accurate. It also allows us to merge things like radiology results. So we transfer our radiology using a cloud-based PACS system, and we bring those results in just as in blue are outside hospital records that are automatically matched, and in the normal color are ours. Same thing with labs, these are our labs, and this is a outside hospital's labs. And what we saw because of this is a really dramatic reduction in the number of repeat lab tests and repeat imaging studies because people just didn't know that they existed. And so by automatically bringing them into the same place, we're able to not only reason about patients a little better, but we're also able to reduce our the cost of care. The next example I'm going to give is around contextual autocomplete. So on your phone, as you type a text message, the next word that comes up is contextual on the last couple of words that you wrote. And so we take a similar kind of strain here. While one of the things that you do in emergency room triage is to document a chief complaint for our patient, but we know things about the patient already. We know their vital signs, and we have a short little blurb about why they're here. And so rather than picking from anything, can we predict the likelihood of any chief complaint? And so right here, you'll see the top 5 predicted chief complaints. And on the right-hand side is a autocomplete where if you type a letter, it orders what's returned here by the predicted probability. And in fact, you can almost always get to the chief complaint you want using 2 or less keystrokes. And what we found is beforehand, we tried a lot of different ways of getting people to document better chief complaints that are structured. Pre is pre-intervention. This is our post-intervention. And you can see that our percent of structured documentation goes from 35% to 95%. We then did a qualitative study of a random sampling of different chief complaints, and we found in the post-study they were more complete, of higher quality, but no real difference in precision. And what's really dramatic is we reduced the number of keystrokes that a nurse had to use from 11.6 to 0.6. And we estimated this saves around 90 hours per year of nursing time, just by using some machine learning to reduce the amount of keystrokes that you use. And so that it's easier to do the right thing than it is to do the wrong thing. And that's that we took that kind of pilot phase of this one small text field, and we thought, well, can we deploy this throughout medicine? And can we rethink what documentation is? So rather than documentation being about billing compliance or medical legal compliance or what have you, can we rethink what documentation is and re-envision it as a way of doing clinical reasoning? Especially since most user studies show that more than 70–80% of physician time is spent using a computer rather than interacting with patients, and has been associated with physician stress and burnout. So can we rethink this whole enterprise and do it differently? And so you saw in the prior example, by using machine learning methods, we were able to make it so documenting using natural language documenting structured text was more efficient than documenting unstructured text. But there's a lot of value in natural language as well. It allows you really a high level of granularity. The problem is there's lots of inconsistent definitions. There's a lot of vagueness in it, where terms are often overloaded. So MS can mean mitral stenosis, multiple sclerosis, etc. So can we do better? So what we've been working on is a way of re-envisioning documentation as purely a clinical reasoning tool. And as you explore data, you automatically document it. And as you explore it more and more, the computer helps you reason more and more, either by pulling more information or making new connections between pieces of data. And the benefit of all this is that you collect structured data, which helps you build better machine learning models to begin with, which allows you to deliver a better experience. So there's really nice feedback loop between collecting structured data and building models, employing it, and giving it back to users. So that is exactly what we've done. We're running out of time here, so I'm going to skip forward a little bit. We also built a couple of other things. One is being able to do information retrieval directly in the interface. So if you type glucose, you can automatically document the last glucose, or you can document things like the glucose range, average value, and standard deviation. You can also do things like macros, where you can do a lot of these different combinations as one big template. And we've deployed a pilot of this. You can see we've dramatically reduced keystroke burden of documentation, quite dramatically for things like documenting conditions, symptoms, labs, and medications. And this is work with David Sontag's team, and as well as David Carver's team, both at MIT. It allows us to do really interesting things. In this example, if you document atrial fibrillation for this patient, it automatically goes and searches OMR, and it pulls up all OMR notes that have something to do with atrial fibrillation. It also makes some associations. Well, if you care about AFib, you probably care about metoprolol, and in fact, this patient's on metoprolol, so we'll show you that. If you document vaginal bleeding, we find procedures that are might be relevant to vaginal bleeding, etc. I do have a video, but I'm going to actually skip ahead as I see I'm running out of my time. I'm going to skip COVID predictions, and maybe I'll end with some open questions in machine learning for healthcare right now. One is around model transparency. As you can see, one criticism of these models is that it's a black box. You don't really know what's happening inside. And we've really been working on ways of helping explain what the model is doing and helping to visualize what it's doing. Creating that latent representation, doing better representational learning is one way of doing that. Because if you learn a good, you can actually explicitly test that latent representation, and then you can use that to kind of explain the whole model. But really, overall, how to do better visualization explainability has been an ongoing problem. The other is around responsible AI. How do you ensure algorithmic fairness, especially when that underlying data might be biased to begin with? And how do you get algorithms to have some notion of social justice? Lastly, around there's this entire field around robust learning. What do you do when your data drifts? When the definition of a disease changes over time, or the definition of a lab result, the meaning of a lab result changes over time. How do you get models, how do you build models that are robust to all of that? Especially when the data might be not always reliable, and that reliability might change over time, or the biases within that data might change over time. And lastly, how do you reincorporate domain knowledge about a subject back into those models? So if you know that it's impossible for a man to get pregnant, can you reintroduce that to the model so it doesn't learn ridiculous things? Or if you know that a heart failure is a type of cardiac disease, can you bring that back to the model so it's not wasting statistical power to learn those relationships? And so I will end there and take any questions.
Thanks, Steve. Just having a little blinker action.
Sorry, if there was a question, my speaker was off for a second. I think I missed it.
Let's see. Do you have any questions?
So this is Junji. Hi, Steve. Thank you so much for this talk. I just have a kind of general question. So if anyone is interested to learn more about kind of these approaches to AI/ML, given the fact that you know, this not necessarily have been part of our kind of core education, and I'm talking about those of us who are not, you know, fresh graduates, then what is the mechanism? What would you recommend to kind of get more familiar with this in order to be you know, sophisticated enough to, for example, have a collaboration with you or somebody who has your skill sets?
I think, you know, just learning about what's kind of going on in the community is always kind of helpful. We run a lecture series on Tuesdays at noon, so actually right before this, which is across all the Harvard hospitals around these kind of topics. A third of that curriculum is around data science and machine learning, where we kind of present a lot of these different topics. So that might be a good way of getting started. There's a bunch of courses out there right now, Coursera and others for distance learning, to get some of the basics around machine learning and data science.
Thank you. And thank you so much. This is really fascinating, actually. It's just really great to see this happening here at BIDMC and all your efforts. So thank you so much for it.
Great, and thank you for having me. Really a great opportunity to kind of showcase some of the work.
Well, I don't see any more questions coming in, so thank you, Dr. Szabo, for that question. And it's 2 o'clock. So Steve, you're off the hook. If anybody's still on and they come up with a question afterwards, please feel free to email Dr. Horn. And then look out for our next research seminar series that will happen in the coming weeks.
Thank you all very much.
Thank you.